Hi, my name is Daisy Huang. I'm a researcher at the university at the Alaska Center for Energy and Power. Welcome to the heat recovery session. Our distinguished panel here consists of Devany, Plentovich, first of all, from AEA, Bryan from AVEC, Gary Hennigh from the City of King Cove, and Beste from AP&T. First, Devany will give you an intro about waste heat usage in Alaska, and then our other speakers will tell you about individual projects that they have in their communities. So, first we have Devany. She's the program manager for both biomass and combined heat and power, both of which are projects I've worked on, so I'm very happy about this because Devany's awesome. And she's been in Alaska for the last 5 years. Before that, she was a mechanical engineer working in manufacturing for the previous 27 years. So, welcome, Devany. I don't know if you want this or, okay.
If anyone's ever seen me speak behind a podium, it's pretty entertaining, so I avoid it. So I start getting so excited about the topic that I start hitting the microphone, and it's a bad thing. So I'm going to talk a little bit, very quickly, about the Alaska Energy Authority Heat Recovery Program. Heat recovery is boring. I really apologize. There's no way to make it exciting, other than the fact that from a renewable energy or energy efficiency standpoint, it is the first thing you should be doing. Paybacks for projects on heat recovery are 4 or 5 years. They just make sense. Hence the title of our workshop is Heat Recovery, Just Do It. Well, we're just going to look at Denali for a while. There we go. Oh, okay. Thank you. Okay, our heat recovery program. The mission is just to increase the utilization of recovered heat from our power plants and other heat sources within Alaska. So most of our isolated villages are run on diesel power plants. In the past, the heat from the diesel power plant just went up the stack. What we're doing with heat recovery, very simply, is gathering the heat that would normally go up the exhaust in the diesel and using that heat to heat buildings in the surrounding area. Very, very simple. Simple engineering, simple topic, and pretty effective. If you're paying $7 a gallon for fuel oil and you're replacing it with basically a free fuel, that's a good savings for the community. So with our heat recovery program, what we do to help further the heat recovery projects is, number one, we conduct pre-feasibility studies. So if a community is interested in either having waste heat if they do not have it, or expanding an existing system if they have extra heat, we will do a pre-feasibility study free of charge for the community to get the project rolling. We also do technical support for project development. We do education and outreach activities just to help people understand the technology. And we will also do a screening analysis for combined heat and power, and I'll talk about that a little bit later. Funding for this program is provided by the state through AEA, Alaska Native Tribal Health Consortium, and the Washington State University in conjunction with the Department of Energy. And I really want to give a big thank you to Alaska Native Tribal Health Consortium. They have been just a very, very active partner. In fact, they have done most of the pre-feasibility work in the state within the last few years. So how do we do this? How do you go about getting a pre-feasibility study? We have an annual prioritization. So we look at the status of all of the existing power plants in the state. We actually sit down, a group of us, go through a list, and we look at power plant audits that have been done recently on what is the condition of the heat recovery system. Is there opportunity for expansion? We look at the RPSU, so the Power Plant Replacement Program through AEA. We look at their priority and status. All of the new power plants get heat recovery if there is a use for the waste heat. We talk to the different utilities, get their input. We look at water and sewer projects that are going in the communities, which is usually one of the highest heating loads in a community. And if there's a water sewer project, we try to work with the heat recovery program to expand it into that system. And then we also look at renewable energy opportunities. Is there excess wind that could be used for heating? Is there excess hydro? Things like that. If we do not have enough information, we'll make individual contacts with the utilities and community to find out the status. And then we send requests for information. So we do this on an annual basis, and we have a prioritized list that results for feasibility studies. The team members of this group that's doing the prioritization are the most knowledgeable on the power plants in the state. So we use the AEA's RPSU group, which is Tim Sandstrom and Chris Noonan. We pull in Carl Rimley and Dan Reitz from Alaska Native Tribal Health Consortium. Bryan, take a bow, from AVEC. Brian Gray and Steve Stasel from Gray Stasel Engineering. We're pulling in a utility rep from the Southeast, and then we also use AEA's regional planners doing a lot of the contact with the communities. So when we need more information, regional planning group is pulled into the discussion. So this is the map, the heat recovery map. Sorry if I'm in the way. So in the last, this is probably from the early 2000s to now, we've done at least 30 pre-feasibility studies, and that's the little red dots. And that's, we have 10 pre-feasibility studies right now that are in development, 18 design and construction projects, and over 34 systems are in operation since 2004. And this is through the Renewable Energy Fund and through the RPSU group at Alaska Energy Authority. So as you can see, we're getting a lot of work done, a lot of projects in place. Some of these are new construction, some of these are expansion of existing systems. But in all of these communities, we're significantly reducing the cost of heat in surrounding buildings. And you guys interrupt me at any time with questions. Okay, pre-feasibility studies this year that are in progress. Aniak, Anvik, Bethel, Chafornik, Holy Cross, Hughes, Klickinik, Kivalina, Caltag, Minto, and Wales. So these are the ones that are in progress, and hopefully we'll see some applications through the Renewable Energy Fund next year. In fact, there might be a couple that are actually, that ANTHC completed and that we have received applications for. I haven't seen the list yet of the new applications. These are the communities, and I'm putting this slide up because these are the communities where we're looking for additional information. What is the status of the existing heat recovery? Is there opportunity for expansion? So if anyone in the room has information on any of these communities, I would like to talk to you more. So I'll give you a second to read through that. So these are the ones that we're just not quite sure what the status is. Now, we also receive a little bit of funding for the heat recovery program through the Northwest Combined Heat and Power Technical Assistance Partnership. This is with the lead agency is Washington State University, funding through Department of Energy. And it's a collaborative of all of the CHP technical reps in the Northwest states. So it's a great opportunity for sharing of experience with combined heat and power, and for just answering if we get questions in an area that we're not quite expertise at, we can find find an expert in the Northwest. So the mission of the CHP Technical Partnership is to transform the market for CHP, waste heat to power, and district energy technologies. So they're focusing a lot on district heating systems, multiple buildings off of one heating source. The key services that are provided are the CHP screening analysis. So if an entity, and it's usually a pretty large entity for combined heat and power, if you are interested in seeing if you can do electrical generation with heat used for heating purposes, we can do a screening analysis. It's kind of a level 1 look at the economics and technical feasibility for CHP. If people have ideas on potential projects in this area, come talk to me and we can talk about doing a screening analysis. We also do education outreach and technical assistance. and poor spelling on project development. So, any questions on the heat recovery program? All right. So, turn it back to Daisy.
Thank you, Devany. So our first speaker will be Bryan from Alaska Village Electric Cooperative. He is the operations manager. He's lived in Alaska most of his life, and he had no interest in sword swallowing. So here, do you want to use this guy or do you want to use that?
I'll try this one.
Okay, and then there's a control.
Good morning. So I'm here to talk about enhancing heat recovery by using marine manifolds. How do you make it go?
This button and aim it at the back.
I work for Alaska Village Electric. We have power plants all around western Alaska, small diesel power plants. 74 Anchorage-based employees. We acquired Bethel earlier this year, 16 employees based there, 95 local plant operators, 49 power plants out in rural Alaska, and 162 diesel generators. Currently have 17 heat recovery systems. Not all of them are in service right now. All kinds of fuel tanks. We buy about 8.5 million gallons of diesel a year, and we have 34 wind turbines serving 15 of our villages. So, as you know, as Devany was saying, heat recovery's really taken off in the last decade. A lot of that's based on fuel prices. Back in 2003, our average fuel price was $1.49 a gallon. In 2013, it was $4.19 a gallon. So AVAC's worked with AEA, ANTHC, some school districts to help develop heat recovery projects in our communities. So AEA developed the Caterpillar 3456. That's about a 500 kW unit with a marine manifold, and had a lot of success in increasing the heat output and maintaining the fuel efficiency. There's a chart of the fuel prices. As you can see, it's pretty volatile. 10 years ago, $1.49, and now we're up over $4 a gallon out in our communities. So, at AVAC, we have over 50 of these Series 60 units running out in our plants, scattered all over the place. They're rated up to 363 kW. They have excellent fuel efficiency. That's why we use them. Fuel is king out in rural Alaska. They're inline 6-cylinder, 4-cycle diesel engines, and they use the Detroit Diesel electronic controls, the DDEC. They got up to DDEC 4, and it increased in horsepower with each revision. So you kind of have different horsepower units out there. We have 1,200 RPM units. They go up to 236 kW. And then we have 30 units at 1,800 RPM up to 363. So in our small communities, they're a good engine for the 300 kW range. There's one of our units in Elam, just to give you an idea what a Series 60 looks like. So during one of our annual discussions about heat recovery, we've been talking about the Series 60 and possibly doing a marine manifold project. Worked with Devany at AEA and Pacific Power Products, Gray Stasel Engineering. We all kind of got together and partnered up and developed a plan, and we were fortunate enough to get some funding from AEA to work with Pacific Power Products and do some testing. And there were three main goals of this testing we had to do. Of course, we had to maintain the fuel efficiency, and we had to maintain performance. We needed to make sure it could still pick up the loads well like they do now. And then, of course, measure the heat output. It sounds kind of like a simple project to just put a marine manifold on an engine and let it go, but we have two different speeds. We have 1200 RPM units, we have 1800 RPM units, and then to try to maintain the fuel efficiency and the performance, Pacific Power Products actually offered up some different turbos to try. So basically we were going to use our standard turbo that we use on all our Series 60s, a wastegate turbo, and a marine turbo. It's water jacketed. So as you can imagine, over at Pacific Power we had to hook up radiators, all kinds of equipment, and get it all ready to test. Had to measure fuel. Kind of skipping over that part a bit, getting down to the test. So we basically did baseline tests with our standard configuration, which is a dry manifold, a dry turbo, just to get baseline on fuel efficiency and performance. This is the results of the tests. We tried 4 different configurations. I told you about the dry manifold and the dry turbo, and then we used the wet manifold with the marine turbo, the wet turbo. Then we had the marine manifold with a wastegate turbo, and we tried using the marine manifold with the stock turbo. And those are kind of the fuel curves. They actually weren't too bad on the 1800 RPM. All the configurations seemed to work fairly close. I mean, obviously some were a little better. And this is a chart showing the heat output. The blue line is our base. That's what our dry configuration is producing. And as you can see, there is a substantial amount of heat increase by using these marine manifolds. So in the end, the best fuel efficiency, the most consistent with our baseline, was the wet-wet configuration. That was a wet manifold with a wet turbo. Pretty similar fuel efficiency. A good increase in heat output. So the results of the 1800 RPM test proved out that the wet manifold with the marine wet turbo configuration maintained fuel efficiency and performance comparable to the dry manifold and stock turbo. So of course, with the varying load was varying heat output, anywhere from 25 to 68% more heat. But if you figure your average load is 150 kW, this displaces almost another gallon of heating fuel per hour during the winter months, or could add up to 6,000 gallons additional, or 6,000 additional gallons during a 9-month season. And that can be pretty significant if you're paying $5 or $6 a gallon for fuel. So if you're in one of our rural communities, and it's a pretty good shot that we got a Series 60 there, you know, it would be something to look into. Well, then we basically had to swap generators and reconfigure everything and get it all set up to run at 1200 RPM. We ended up doing 3 tests here. The 4th one, which was the stock turbo with the wet manifold, it was almost a non-starter. It couldn't get enough boost. It didn't even get out of the gate. So these are the fuel curves. You see our baseline up there. The wet wastegate configuration seemed pretty close, and the wet manifold with the marine turbo, it kind of fell on its face. Didn't do as well. Actually, let me back up. So I guess you kind of need to see the point there of how the wet configuration really didn't do as well for fuel efficiency. Although on the heat output, it definitely did significantly better. That's a chart showing the heat output at 1200 RPM. But like I said, fuel is king. It's what costs us the most money. So we maintained going with the wet wastegate turbo due to the fuel efficiency. And that again is the additional heat output. So the results were the marine manifold with the wastegate turbo configuration maintained the fuel efficiency and performance that was comparable to the dry manifold and stock turbo. Heat output increased 25 to 68%. Actually, that's not correct. It was 2% to 51% at 1200 RPM. Of course, it's running smaller or slower. It doesn't put out as much heat. So at about a 75 kW load, it'll displace about 1/3 of a gallon of heating fuel per hour, or about 2,500 additional gallons for a 9-month heating season, which is also can be very significant at $5 or $6 a gallon for fuel. Here's a factory photo of a Series 60 with a marine manifold. I guess some things I'd like to add to this is, you know, some lessons learned here. I mean, obviously it's pretty significant to test your units before you just go throw a marine manifold on there. You really don't want to lose out on your fuel efficiency. And as you can see with the different configurations, it can make a big difference. So some other marine manifold projects we got going on. We built a new plant in Stebbins. Just put in 4 Cat 3456s with marine manifolds. Hopefully next year we'll have a heat recovery project being installed, and that's going to be a real big benefit to the community. In New Stoyhawk, we actually did a retrofit project on a 3456. The school district there is going to be running their distribution piping over to the plant pretty soon, and they'll start getting the benefit of heat recovery. And that's it.
The pictures of your plants look so clean. I'm impressed.
Oh, I'm sorry.
If you have quick questions, we'll take them now, but if you have bigger ones, we can hold off. Do you want to? Oh, sorry, you probably don't need that. Do you want?
Thanks. My question, I guess, is why not just using off-the-shelf marine gensets? I mean, these are used in commercial shipping, processors, or things like that. Is there anything just to compare something that's already built, and this, instead of using seawater through the heat exchanger, use whatever your load is? Is that, instead of retrofitting, or at least if you're going from new construction, why not just use a marine genset? Is there something, I guess, out of that?
Well, we actually got 50 of these Series 60s already out in the field, so you can get a marine manifold parts and that for about $15,000. So probably installed, you're talking about $25,000. For us to install a new generator set out in the field, it's well over $250,000. So.
Can I add something, Mark?
Sure.
Yeah, also I wanted to point out that the marine manifold engines that are currently provided by Detroit Diesel, they're all 14-liter engines. None of AVIC's engines are 14 liters, so that was part of the testing. It's taking a 12.7-liter Series 60, which you've got, what, 53 of them at both 1,200 and 1,800 RPM, and then working with Pacific Power Products, the Detroit Diesel rep in Anchorage, and taking those parts off the 14-liter and putting them on a 12.7. So it was kind of an apples and oranges thing, and you know, so trying to use existing 14-liter engines would be significantly more expensive and a change in the infrastructure from what AVIC has been using.
Thank you, Steve.
So I assume that in your evaluation, you looked at sort of the crossover point between the efficiency of generation and the amount of waste heat recovery being gained, because obviously, you know, you might be able to take a slight hit on the generating efficiency if the waste heat increase was enough.
Right, but fortunately, as you saw, our fuel efficiency basically stayed about the same. We didn't take much of a hit at all in fuel efficiency.
Well, it looked like there were a few where you did take a hit, but the waste heat recovery was much greater. I don't remember which example it was, but it seems like potentially it'd be worth taking even a bigger hit on the efficiency if you can use that waste heat. So I assume you looked at that stuff?
Right.
Okay. My second question is, so you're getting a higher quality of heat. You're increasing your temperature of your waste heat recovery as well. Is that a significant factor over just water jacket waste heat reclamation? I mean, that's going to typically be like 160 degrees. I assume with the wet manifold, you're probably getting up well over 200 degrees.
For heat output?
Well, the actual temperature that you can achieve.
Oh, sure, sure. We're getting a much better thermal load out of our engine now.
And then the final question is, I mean, these are relatively small, but I mean, there are some technologies that allow you to actually co-generate electricity off of the waste heat. Have you looked at that at all?
I don't think we've seen any viable
We have a presentation coming up.
product like that.
Okay. So yeah, I saw one more hand, and then I'll have to wait. We'll have to wait until the end.
Good. Well, hey, thanks, Mark. This is, I find this extremely useful information, and the fact that AVAC continues to lead the charge on these fuel efficiency issues is really good news. One question, I may have missed it. Do you have a feel for what the rough cost has been to convert the 3456 to marine manifold and also the Series 60 to 1800?
It's about 30,000 to convert the 3456, and I would say about 20. We haven't done a retrofit on a Series 60 yet, but I'm thinking 25,000.
Okay, good. And I guess so. There was a slide 15. I don't know if you can find slide 15. It sort of reflected sort of the characterization of the fuel efficiency of the Series 60 to 1800 RPM. Or that might have been at 1200 RPM. I'm wondering, back in some early days on the 1200 RPM Series 60, there was some experimenting going on with a smaller 11.1 liter turbocharger. I'm wondering, in your evaluation then at 1200 RPM, was there that turbo available in a marine manifold or a wet version marine manifold? in other words, converting the 12.7 liter engine from the 12.7 liter turbo to 11.1 liter turbocharger. Was that turbo maybe available in a marine manifold to perhaps increase some of that efficiency and output?
We actually recruited Pacific Power Products to assist us in selecting the turbochargers because, of course, you have a wide variety of them, and we only had funding to do so many. So they actually chose the ones they felt would do the best.
Good. That's it. Thanks, Mark.
Thanks, John.
I was involved into the testing, and one of the criterion on the turbochargers selected is that they had to be available long-term in the existing market, and so Pacific Power selected the 4 turbochargers that they felt had the best likelihood for being successful, but most importantly were available long-term and weren't going to be required to be remanufactured from things that didn't exist.
Thank you. Thank you.
Okay, thank you.
All right, thank you, Mark. Our next speaker, if we follow the agenda, is Gary Hennigh. He's from the city of King Cove, and he's here to tell us about a heat recovery success story in King Cove. So, do you want to stand up?
Which one?
Here's the clicker forward, back, and there's a laser pointer.
Okay, good morning. Gary Hennigh, City of King Cove, and I'm not going to certainly get into the technical details that Mark did because I'm not smart enough to really understand them. That's why in my case you get to know people like Steve Stasel, probably the smartest guy in the room that can tell city managers how to do things and who to ask money for and what you're going to accomplish. As you can see, I can't even get this. All right. Oh. Which one? Okay, as you can see, I'm challenged. So, what's new in King Cove? We're going to talk today about recoverable heat, a little bit about how and when it happened, who's benefiting from it, and the value of that recoverable heat. I've been told I can't really talk much about the thing that we're most in the news for, and that's, most of you probably know, we're in this ongoing issue about wanting to build a road between King Cove and Cold Bay that's got quite a controversy. I also was told I can't brag too much about King Cove being the premier small run-of-the-river hydro running place in rural Alaska. That'll all come later. So today I'm going to, as much as I can contain myself, talk simply about recoverable heat. But let's first of all talk a little bit about King Cove. This is an aerial view, and the 2 boat harbors where about a third of the town lives. This is the third of the town that's not a great photo to show where our new power plant is. We'll talk more about that. Another third of the town, 625 miles southwest of Anchorage, almost at the western end of the Alaska Peninsula. This is downtown King Cove, the large Peter Pan Seafoods, the largest wild salmon cannery in North America. For those of you that go back in time, Governor J. Hammond, 1964, tried to land his float plane there in Heart Lake, crashed, broke both of his ankles, was weathered in King Cove for quite a few days. In his autobiography on page 191, he talks about that day in King Cove when he should have never tried to land his plane. A lot of alcohol and a lot of people staying up around the clock for a few days got him nursed back into health so he could fly to Cold Bay and get back to Anchorage. Chamber of Commerce Day in King Cove. This is our first boat harbor. This is predominantly the local residents of King Cove, their salmon fleet. These are all crab pots. Back in the heyday of crabbing, before crab rationalization, King Cove was a very happening place. It still is, just not at the same level. The other new boat harbor that you can't see is off here to the side. King Cove's been around 103 years now. I already said 625 miles southwest of Anchorage, population of about 940, second largest city in the Aleutians East Borough. I already talked about Peter Pan, incorporated in 1949, 10 years before the state even became a state. It's been a first-class city status since 1974. It's a pretty unique place. Recoverable heat, when did it happen? Well, a lot has been happening in King Cove in the last 15 years, and out of that came certainly recoverable heat. But before we got to that, it was really starting with a new diesel power plant to supplement the hydro that came online in the mid-90s. To the forward-thinking people that I work for, the mayor and the city council, they started talking about where, if we ever got the money, and until we got Steve Stasel to tell us where you'd build your diesel power plant, we started looking at land that would be close to where a new school was being talked about, within about 2 football fields away. The city went ahead and purchased the land on speculation that at some point in time a new diesel power plant would show up there and that a new school would show up there. 5 years later, that all started to come to fruition as it makes sense. And it was the 2009 report that Steve did for the Alaska Energy Authority that talked about a new diesel power plant in King Cove and a lot of other things that would support that new diesel power plant, of which certainly recoverable heat was one of the components that was put in the cost estimate and said, if you're going to build the project the right way, then you're going to do what it takes to keep recoverable heat as a viable option. So our new diesel power plant, with the great help of the Alaska Energy Authority, the Denali Commission, and the city of King Cove, spending real money, were able to make that happen in 2008 and 2009. About $3 million. The key thing is that the 2, 3, 4, 5, 6s, which Mark talked about, have ended up being very important in actually what's now our second phase of the waste heat, but those were part of the original design that went into the system. Again, you can see the significant component, recoverable heat and an electric boiler, and that was to help both with the frequency of the surplus hydro that we have from our 1 hydro facility, soon to be 2nd hydro facility, at the same time to be capturing the heat off of the diesels. Of course, the SCADA system, and for us, the best sound of the diesel plant is no sound, because that simply means that our hydro is doing what it does best for us. This is the new diesel plant. Inside the diesel plant, nothing that exciting that you haven't all seen. This is the electric boiler that has become very, very important for what it does for us. And again, Steve Stasel is going to be the type of guy that will tell you more about all of what it really does. I simply know that the results that it means has real dollar value. So our first phase of the heat recovery system in 2009, when we hooked to the new King Cove school, 40,000-foot school, that since that time, phase 1, we have been displacing about 22,000 gallons a year, and in those 4 years, at our current price of about $4 a gallon, that has been over $90,000 annually and more than $350,000 savings in just those 4 years. We share those cost savings between the city and the end user. In this case, it started out with the Aleutians East Borough School District. We entered into a formal sales agreement that has a cost formula that at the end of the day basically says 60% of the value of the displaced diesel that you're getting at the school comes back to the city to put into our utility fund. The user gets to benefit the other 40% savings by not paying for the cost of diesel that they don't require. Again, this formula, the logic behind it came from Steve and his people. It works well, and the end user, the Aleutians East Borough School District, has been very pleased with it. This is just into the calculations. The significant thing is 1 month when you got 30 million BTU, you convert those BTU into diesel gallons. It basically says 3,000 gallons of diesel in this particular month was avoided because there was the 30 million BTUs. At $4 a gallon, that's $12,000 savings in just 1 month. Of that $12,000 savings, 60% of it comes to the city of King Cove, the other 40% back to the Aleutians East School Borough District. This was phase 2. This was another concept design report done by Steve and Bryan Gray that basically, in working with the Energy Authority, said, we think King Cove even has the potential for more waste heat. They went ahead and did the study, and this is a bad photo. I apologize for that. I'll have one to clarify in a second, but down here is where the power plant is, the new school, and the other facilities that we recently hooked up. This is the rest of town. That's Heart Lake, where I had made the comment about Governor Jay crashing his plane a long time ago. This is a better photo. This is the diesel plant that we looked at. From the diesel plant over here to the school, that was phase 1. A couple football fields in length. Phase 2, the report that I just showed you, was to then take the system, go up to the new King Cove Clinic, and at that point it was going to stop right there, but when Steve and others realized that maybe we've got more recoverable heat available than we thought, and we talked very nice to them in AEA. They said, all right, maybe we can add this unit, and we can add these units. So in the end, phase 2 was not just more power to the King Cove School, but it was, when I say power, recoverable heat, it was more recoverable heat to the clinic and to basically 11 living units. Diesel plant from another angle, we looked at that. This is the school that we've talked about. This is the clinic, and these are the AHA Housing, Aleutian Housing Authority. So, 2012, AEA's recommended #1 priority. Back in those days, ARA funding, everybody remembers what that was all about. We happened to be in the right place at the right time. The cost estimate to do the expansion was $306,000 with a 2.9-year payback. In the end, the project actually was about $350,000, but that's because we added in the other units I talked about. And it was basically to install marine jackets on the 3, 4, 5, 6s, which Mark talked about, the 860 feet of additional piping, which actually ended up being a little bit more than that to extend to the other units, and then additional recoverable heat to the King Cove School. So the project got completed in 2012. It was a combination of an AEA force account and city labor and city equipment. And by the fall of 2012, phase 2 was brought onto line. And what it means now is the King Cove School now is getting 25,000 gallons of avoided diesel because of recoverable heat. Actually, this number we believe is going to go up a little bit more. The King Cove Clinic is getting at least 5,000. We ultimately believe when the system is tweaked enough, it can be up to as much as 8 or 9, and the Aleutian housing units are getting about 7,000. So very conservatively, 37,000 gallons of diesel are being avoided in King Cove today, and realistically that number is probably closer to 40 to 42,000. So the rest is pretty simple math. Actually, today's price of fuel in King Cove is $3.75, so I'm getting soft in my old age and use that. But this year alone, about $140,000 is being saved. Again, the city's 60% of it. The users get 40%. 20 years, I simply used an arbitrary 20-year payback. $1.6 million in present day value is going to be saved or additional revenue into the city's fund because of the recoverable heat value, and $1.12 million for the various users to spend as they see fit. Future possibilities, we believe that we even have more recoverable heat because of the second hydro project that we're getting ready to build, and that we also believe that we're going to be selling some additional diesel power to the large processor in town, which again will create more heat that we have in our recoverable heat system. And we already have 2 more places in King Cove that we would like to expand to. Actually, it's one right now. It's the King Cove Community Center, which is going to be eventually turned into a senior housing complex. Picture of Mayor Hennigh Mack. He's been the mayor 12 of the 24 years I've been their city manager. And the reason for showing his picture is working for a mayor and the city council who look around and say, you know, there's new things happening, there's new technology. If it works in other places, yeah, King Cove, we're way out here at the end of the Alaska Peninsula, but let's try it. And again, that's where knowing people like Steve have been very important. We also, with the Energy Authority, have been good friends with them. Alan Fetters, in particular, on this project, made a difference of supporting us and getting the project done. He was very aggressive, moved a whole lot faster than probably I was ready to move, but that's why I'm lucky to have the lady sitting up front, Bonnie Foltz, who's my administrative assistant, who worked very closely with Alan to make that project happen. I think in summary, I simply would say that King Cove has been able to know that sometimes you got to create your own opportunities, be in the right place at the right time, be willing to spend some of your own money, be willing to take a chance, as long as people, again, like Steve and others tell you that it's a calculated engineering real-world chance. Do it. Most of the time, if you do it right, you end up coming out okay. Learn how to be humble. I sometimes have to force myself on that, but I've come to know that's a good trait. Most importantly, be able to say thanks to the people that help you do these things. Thanks to the governor, the state of Alaska, the Energy Authority, people like Steve Stasel, and the residents of King Cove for being willing to do such things. So that's my story.
Thank you. Are there any questions? All right, so we will move on. Is this off? Okay. And our last speaker today is Ben Beste from Alaska Power and Telephone. He's going to talk about a project on waste heat recovery in Tok to generate power.
Thank you. Good morning. See if I can do a little better here. My discussion is a little bit about Tok's experience in the use of an application of a green machine provided by Electrotherm and, well, provided by ASEP, supplied by Electrotherm.
Closer to the mic, please.
Yes, thank you. AT&T is a company that provides power and communication services to many communities in Alaska. I'm a mechanical engineer for AT&T. I work on the power side generally. The opportunity to reduce costs, to improve performance, to make these systems more efficient is always one of our first goals. Heat recovery is used in most all of our plants, not all. We supply heat to local schools and heat recovery loops there. We use heat for space heating in our plants. The use of an ORC has been something that we've been discussing for a long time. The opportunity to work with ASEP and the installation of the ORC in Tok was very advantageous for us. This is the interior operations for Alaska Power and Telephone. Oops, I'm sorry about that. Our Tok is there. There's Fairbanks up in the corner. Tok is down towards the middle there. We have our primary customer service center there. Our maintenance shops, our utility.
There's a laser pointer in the middle if you want to use that.
Thanks, AC. Our maintenance shops are storage facilities for both the power and the communication side. These other locations you see on here are areas that we service providing power and communications. Tok services them, plus others up to the North Eagle and further up into Allakaket. The milestones of the ASEP ORC project were started some time ago. They began with the opportunity that ASEP was given with a grant from AA to work with the Tanana Chiefs Council to purchase an Electrotherm green machine for testing. The ASEP proceeded by taking the grain machine, receiving the grain machine and taking it to Fairbanks and operating in their laboratory there for some time, proving out its capabilities. Second phase of the work was a secondary grant from the AA to continue the study of the green machine in a diesel plant operated in a Tanana in a TCC affiliated community. AP&T has worked with ASEP many times in the past, so they didn't hesitate to come to us and ask us if we'd be interested to work with them, recognizing that Tok was such a community and that had a operating diesel plant that would support the installation of the green machine. So we went through a process of discussions and negotiations and finally got a contract to do the work, and in 2013 we went ahead and installed and commissioned the green machine in Tok. It was put into operation in August 2013. Unfortunately, in October of 2013, it threw a bearing and that took it out of service. It's been out of service since, and AP&T has been working with ASEP and the Tanana Sheets Council and Electrotherm to come to some resolution on how to move forward. This is the time sequence a little bit. We started the whole thing in April of 2012, and the study that we were committed to work with ASEP was through the end of 2013. We had hoped to be able to continue the operation of the green machine into 2014 so that we could actually get a sense of how it operated through the winter months and into the summer months. So we don't really have a lot of experiential information with the green machine, but not as much as we'd hoped to get. We were given a budget of about $175,000 by ASEP to get the equipment installed, and our budget estimates were a little bit higher, but we had some contingency in there, so we felt we could move ahead, and we did. Our scope of work included the engineering and design of the what was required to install a green machine in Tok, and then the installation and construction aspects, which were to replace the small diameter heat recovery piping that was in the power plant, replace the low capacity heat recovery heat exchangers that were in the power plant, rebuild a heat exchanger, and add thermostatic control valves on the units that you have external radiators. And throughout the piping system, we added isolation valves so that we could more efficiently run the heat recovery system with considering the best performance of the green machine. We installed the ORC. We installed the fittings for installed the piping to connect it to the recovery system. We used one of the existing wells to provide the cold side connections to the ORC and connected the piping to that. We installed a drain field behind the power plant to dump. It was an open system on the cooling side. We took well water, ran it through the green machine, and then displaced it in the drain field. And we worked with ASEP to install a sensor and monitoring system so that they could perform the balance of their study, which was to measure the performance of the green machine. And then we were to operate and maintain the machine through the period of the study. This is Tok. Might all be familiar with it. The Tok is a pretty good size area. We service. This is all connected, grid connected. Actually, the grid goes out further. It goes all the way down to past Mentasta to Chichina. It goes out to Tedlin, and it goes over to the village of Tanacross and out further than that to Dot Lake. As with many Alaska communities, it's pretty well spaced out. It's to give you an idea, if you're not familiar, that grid is a 1 mile by 1 mile grid. So even though it looks like a fairly tight community, it's quite widespread. This is a little bit closer view. It shows the power plant. It shows the main intersection coming into town. That's the Alaska Highway. That's the Glen Allen Highway. The power facility is right here. This is a closer view yet, and it shows our main offices is here. This is our power plant, diesel tanks, power plant offices, maintenance and storage, and this is a comm center here. It's got all the telephone equipment in it. In addition, we have a residence here for the plant operator to live in. This is a scheme of a simple floor plan of the powerhouse, just to give you a sense of where the equipment is arranged. We have offices, main office, entry office, switchgear, 5 units side by side in the main gallery. In a newer portion of the building, we had a C-175, Cat C-175 located. Balance of the area is driveway and storage. And this is an addition that was put on even more recently that we have for storage. This is an outside view of the plant. Same diesel tank. This quantity hut here is the original building. Added to that building later was the structure that provided the cover enclosure for the C-175, and on the end, the newer storage area. This is a simple schematic of the heat system in the plant. The blue lines represent the cold water that is pumped through the plant, providing cooling to the units. It's all open circuit, comes from 3 different wells, connected onto a header, ran through the different heat exchangers, and then discharged into a drain field. For the ORC project, we constructed on our well number 3, we constructed a new drain field and isolated this well from the rest of the system. A little closer view of the main trunk line of the system. These are our generating units. Unit number 7 is removed here because it has been removed from the power plants in a different. It's located in a different station now. The red lines represent the glycol lines in the plant. The glycols, the heating system is heated by the jacket water of the generating units. That jacket water is the jacket water goes through heat exchangers, and then a separate glycol system is used to circulate water through the plant. In our heat recovery system, that heat before the installation of the ORC, the heat recovery system was in place. It had been cobbled together literally over many years and served primarily to provide space heating to the plant and the adjacent buildings and structures. The residence, the comm building, the maintenance shop that was on shown earlier. This is a portion of the detail that shows the electrotherm installation. It's got the same red and blue lines, plus it has the purple lines that show the control and sensor connections that ASEP installed to monitor the performance of the ORC. And it shows the connection onto the grid. We go from the electrotherm machine with 480 volt out into the yard up to a pole mounted transformer set and raise the voltage to transmission level. As kind of discussed earlier, we did many modifications to bring the plant up to a specification that would actually support the ORC more effectively. These included increasing the pipe size, installing valves, rerouting everything. One of the changes we made on several different units was the installation of newer, higher capacity heat exchangers. These heat exchangers are on the recovery side, so the engine coolant runs in through one side out, and the heat recovery system runs through the other side and out. This is our unit number 3 before the installation. The heat recovery was we did have heat recovery. It was through a shell and tube exchanger located at this point. After the installation of this exchanger in that location, this is what it looks like now. Give you Another feature that we included, another improvement that we included were on the units that had external radiators in order to avoid the heat losses that we expected in the colder months with the operation of the ORC, was the installation of thermostatic valves. This was a shell and tube exchanger that was in the circuit for unit number 4 before the installation, and the same with the installation of the valve. Same changes throughout the plant. Jumping ahead here a bit. As with number 3, we did the same kind of change with number 4. This is a before picture with number 3. And to the right, there's an after picture with number 3. Pardon me, after picture of number 8. Number 9, similar. Can't quite see the exchanger in this one. This little blue exchanger was crowded up, a very small unit. I think we got it out of surplus someplace and stuck it on here just to get us a little bit of heat out at one time. For the ORC project, though, we recognized that we needed to do much better, so we ended up crowding it in over here. You might get a sense. You might look at this and get a sense that this was quite an interesting challenge, fitting all of this equipment into the space that was avoided there. We had to move many pipes to put equipment in and realign components to get everything up in there. It took the work started in June of 2013, and we finished in August of 2013. This is unit number 7. Unit number 7 was C175. It was in place at the time. It was put in place. Well, at the time we installed the ORC, there was no decision at that point to move the ORC out of Toke. To move the C175 out of Toke. So we built into the C175, fully expecting to use it. There was a need in another one of our facilities, Haynes, that justified taking the C175 out and moving it there. So it's a vacant spot that we'll eventually put another machine into. The heat recovery exchanger is in place and will be used when that time comes. Again, in this location, we installed a thermostatic valve. As just discussed, we ended up having to put in all new piping. I didn't have a before picture here, but if you can imagine this wall with none of this piping on it, that's what the before picture looked like. The piping, this 4-inch piping that's in here now, replaced the 2-inch piping that was down in the trench that looped the heat exchanger that you see up there into the rest of the system. Way under capacity for our needs on the ORC, so it all got changed out. To get the 4-inch pipe over there, we needed to go over this garage door. And that installation cost us, well, added the additional responsibility of having to raise all of our expansion tanks on the engines. Another little bit of work that had to be done. Gracious. This is a side view of the C175. The green machine is located back here. It's aptly green. It's sitting next to the step-up transformer that was associated with the C175. This is a little different view. You can see the heat side supply and return piping nested on the floor here. This conduit is the power conduit. Goes back to the disconnect switch. This is the other side of the C175. This one to give you a sense of where the cold water piping comes in from the well. And this location here is where ASAP set up their monitoring and their monitoring equipment. This panel's open here because that's where we connected to the Ethernet. ASAP was able to locally monitor with the devices that they had and what they had on as applications on their computer, so we could at any time really get a sense of what the machine, how the machine was performing. And ASAP was monitoring this at the same time in Fairbanks at the university, and data collecting. The green machine itself has a very good HMI human machine interface that provided current status of all of the system, plus data. It had its own data logging system and allowed us to track performance. This is a front view of the. This is a view of the front door of the control panel, and that's the HMI right there. This is the internal. These are a couple of internal views of the ORC. This is the cold. This is the heat in and heat out. Heat in and cold in, and similarly out. Here we've got the reservoir tank for the refrigerant. We see heat exchangers here inside the cabinet, and over here we have the control panel. This is the other side of the machine. Control panels here. Cover is removed. You can see the heat exchanger. And this is the expander, and below that is a belt-driven generator. This was the data that was collected. This was some data that was entered after when we initially started up the machine. It had we ended up using this hours for our calculations, so we say we had 1017 hours on it when it started. When we put it into service, it immediately produced 24.5 kW. It was being fed 176 gallons per minute, but up by the flow through the machine reduced that flow to about 150 gallons per minute. The temperature in was 185 degrees, basically the jacket water temperature of the units. Cold water in was 65 gallons per minute. This was a limiting factor in the operation of the performance of the machine. This is the best that we could do with our well pump. Temperature of the water going in was 35 degrees. This was actually very good for the machine. The differential between the inside, in and the hot side and the cold side is what gives you determines the power you get out. This matrix up here is the status of the valves in the heat recovery system. As I discussed, we put isolation valves on all the different exchangers so that we could bypass them and avoid the heat losses that might occur by running the heat recovery fluid through those exchangers. This is the two units. This was when this startup occurred. We were running unit 4 and number 9, and this was the conditions of 4 and 9 at that time. Kind of boils down to what this discussion started with, which was the pros and the cons. As discussed earlier by others, the utilization of the heat that comes off of these machines, the diesels in this case, or any other system, is valuable energy. Utilizing it for anything other than just heating the air around it is money in your pocket. We estimated the annual generation from the green machine based on initial information that we gathered to be about 135,000 kWh per year. We figured the fuel savings would be about $37,000 per year. As Devany mentioned earlier, that's about a 4-year payback for the installation of this machine. For our purposes in Toke, we saw this, even though we produce about the same amount of energy and more in the wintertime, summertime is going to be the best time for us to utilize the ORC. We don't have any other demand for the heat. We don't do any space heating, so all the heat can go through the ORC. So our best performance would have been seen in the summertime. Wintertime, we assumed we'd have lower production. We were putting in place, what we could do to improve. It's pretty hard to heat up some of these spaces that we have because they're open most of the time. But we were going to do what we could to reduce the heat loads in the space heated areas. In the time that it ran, it produced about 10 megawatt hours in the 2 months of operation, and that saved us about 700 gallons of fuel. I wish we had much more data that we could have presented. It just didn't work out that way. Perhaps the next time I have an opportunity to talk about this, it'll be much different. As to the Electrotherm green machine itself, I have to say it was compact, very well built, easy to install, but a caveat there is if the system is ready to accept it. We went through quite a bit of work to put the green machine into service at Toke. if you were contemplating something like this, you would want to do it in the early stages of design and construction on the project, so you didn't have to go back and rework the plant to fit it in. Very easy to operate. One button operation, literally. Got great support from the factory. They worked through us with all the issues that we had during the installation and startup. And even though we had some trouble with the machine, we continue to have great support from Electrotherm, and they're interested in continuing with some way to move forward in taupe. On the negative side, yeah, I think we've talked about all of those, but there are some things. The machine does not work without some expense. You have an increase in your parasitic loads. The pumps that move the fluid through the systems have to be, the kW that goes into the pumps has to be taken away from the kW that is produced by the machine. It's a balancing act. The pumps for the machine run much harder than they do if the machine wasn't there. So the mean time between replacement of the pumps is going to be reduced. I mean, we're going to have to replace those more often. We used well water to provide the cooling side cooling side input. That was convenient and I think really worked well for the purposes of this installation. Moving forward, we have other demands on that well system, and it may not be the best way for us to move forward. We might go to a different type of cooling in the future. Next thing here is space. The cooling. The green machine is a very compact unit, but you can see the piping running into it. It ended up utilizing quite a bit of our floor space when it was in place. It wasn't too bad because it was nested up against the side of the unit number 7. But when unit number 7 wasn't taken out, we introduced a playground worth of things to jump up and over to get from one place to another in the shop. That should be looked at. We would probably consider, in fact, we are considering the next ORC installation to be an external installation where we pipe outside of the building, have all the ORC and condensing equipment outdoors. And as discussed before, the operation of the ORC, in our case in Toke, competes with the space heating requirements during the winter. In regard specifically to the green machine itself, the green machine installed in Toke was an early version and was obsoleted almost before we got it. As such, it was a challenge for the factory to help us. We can sell you a new part, but the part isn't probably going to last any longer than the part that you have to replace. So is that really a wise decision to move forward? Maybe not. Toke is a long way from the factory, and the factory support was wonderful, but communication was kind of a challenge. Support from the factory was not, couldn't be instant, which is frustrating when you're in the middle of Toke with a broken machine. And to complicate matters further, the engineers and technicians that were helping us from the factory because this machine had been obsoleted, didn't have the information necessary at their fingertips to really help us. Took some digging on their part, which they did. It's been replaced with newer versions, and many, many improvements have been made. The short lifetime that we experienced with the ORC that we used in Toke has been far exceeded with the units that are in service now provided that have replaced it. The only other thing I have to say here is it is a system that's not very familiar to anyone in the areas that we service. It has it's a thermodynamic process. As such, it uses a thermodynamic fluid. That fluid has to be handled by people who are trained to handle that type of fluid. The refrigerant is not something that you can go to. People are not necessarily available to help you with a refrigerant leak. we don't have in our AP&T staff anyone who's certified to work on refrigerant systems. So that becomes a bit of a challenge, especially if you need to have a solution right away. And when you're in Tok, it's fairly easy to get there. But in some of our installations, it's not such the case. So that's something else to consider with the installation of a system like this. Man, I got fast fingers. Any questions? I'd be glad to answer them. Okay.
What is the anticipated service life, or what's the anticipated service life of the model?
They're seeing hours in the models that are 20,000 hours and more. There's really the idea is that with proper maintenance that they won't really need to have. They have an infinite lifetime. Recognizing that there are components that do wear out at 25,000 hours. The expander component is actually changed out. That's the part that failed in our unit. The expander has been changed in the newer designs, and the units that are in service now are seeing, like I say, they're plus 20,000 hours in service. They have the factory recommended maintenance on is a replacement of that expander at 25,000 hours. It's a major expense, but with that change, the unit will continue to operate.
What is the minimum generator size? I think that's probably what most people will relate to. I know it takes a certain amount of heat to make these things spin.
That's a question I think I'll defer to the electrotherm representative in the room here.
35 kilowatts is the smallest you can make. It just depends on what flow or temperature you use. Oh, okay, engine genset, yeah. We can do multiple small units, or we can do 500 kilowatts is about a 20 to 30 kilowatt output. 800 kilowatts is our 65 kilowatt unit, and then if you have a meg or a meg and a half unit, you could be at 110 kilowatts. So we have 3 different sizes. Right, or if you have multiple engines, we can do. We actually become the radiator. So if you have multiple engines and you do a centralized cooling loop like these gentlemen did at Tok, we can do multiple engines that are smaller than 500 kilowatts.
Thank you.
I don't know if this is for Ben or for Daisy, but how did the actual efficiency output of the unit compare to what was expected from the unit before it was run?
I'm guessing Daisy and the ASEP team have a better sense of that. My only input is that we really didn't get a long time to track record it, and I don't know that we have a solid answer for that, but I'll defer to Daisy.
In the ASEP lab testing, we tested it at full, supplying it with all the heat that it could take, and it performed very well, performed exactly up to nameplate. At Tok, they didn't have enough heat to feed into it, and so they produced less than nameplate, but it did perform as expected.
And that's like about 7% efficient.
Right. Any other questions?
Well, I don't want to divert it too much, but since we're talking about combined heat and power, and there's probably a number of experts in the room, I'm wondering if folks have any experience with micro turbines and what thoughts are on that.
Are there any questions about the ORC? Because that's a little different field.
Well, dovetailing the ORC system looked like you were just picking up jacket heat. Obviously, one could extract more energy if you brought in the marine water manifold and get more heat, and so maybe need less than 500 kilowatts to support one of your machines.
Yeah, if you do the jacket water exhaust, you probably do 300 kilowatt, 1 to 1, we
did look at the option of putting in stack exchangers. The cost and potential complications of doing that kept us from doing it. But again, if you were putting a plant design together from the ground up, it would be something you would want to incorporate, especially with the idea of operating an ORC, because that heat that's three times the amount of heat that you get off the jacket water system.
I'd like to ask a question to the electrochem. So have you had catastrophic failures at any other sites around the world? And how many of these units, and what are you going to do about this guy's problems? I mean, it seems to me like yeah.
Yeah, this has been an unfortunate situation for all of us. This unit was bought in 2010. It was well before our commercial launch of a product. I joined the company in 2010. It was the first unit that we built of this configuration, and it was basically sent to a university to do some lab testing, and then it ended up in a 24/7 situation, which we didn't really fully understand as we sold that unit. So fast forward 4 years later, I have 42 units out in the world. We have 250,000 hours. I have very satisfied customers. Like Ben said, at 20,000 hours, you can replace the expander. It's basically, we give you a rebuilt expander with new bearings and a new seal set in it, and we swap out the componentry. I have 2 sites that are at 20,000 hours now. Like I said, 42 units across the globe in Czechoslovakia, Italy, Germany, Romania, places where people don't speak English, and I have to keep them operating, and I do. So this chapter I will close, and we will have a new chapter. Unalaska right now is installing 3 units. Literally next week they'll be commissioned. So that generation of machine is what you will see from Unalaska, and I will stand by the product. I talked to Bob Grimm last night. We wanted to give a free machine. Before this got moved to a 24/7 application, we wanted to give a free machine to Toke, but it wasn't, the utility couldn't pay for it over time. I said, I will give you a brand new machine, just pay for it over time with the diesel savings, and the utility couldn't work that out. So that's why we're in the predicament we're in. But we talked last night. They think they can get us some revenue over the course of many years to pay back for the machine. I would like to give them a brand new machine. That's what we're working through.
I don't understand. Free machine, I don't understand the word free.
Basically an updated machine. It's called block. It's a block 5. The free machine part is, this was sold for a $90,000 piece of equipment. I don't sell $90,000 piece of equipment anymore. They're $160,000 to $210,000. So we'll give 100% of the credit back, and I'll just get paid for the delta. That's all I want.
All right, I just want to wrap up with one closing statement that for people that are considering heat recovery, your first use for heat recovery is heat. Do you have buildings surrounding your power plant that you need to heat? A heat recovery system supplying heat to a building is probably 80 to 90% efficient. Only consider electrical generation if you have absolutely no heating use for your recovered heat. So an electrical generation is maybe 5% efficient. We hear stories that maybe some of the newer generations are 15% efficient. So you're looking at 15% efficient for electrical generation and a very poor quality heat coming out of that for heating versus using your recovered heat to heat buildings at 80 to 90% efficient. So number 1, heat recovery goes to heat buildings. If you can't do that, then maybe consider electrical generation. Okay. All right. Thank you very much for coming to the heat recovery session.